checkpoint that you just took. This is the complicated right before the test checkpoint to really push your understanding of the content we've been talking about. So in each case above, a mass, MA, is hanging over the edge. So that's this one. So this is A in each case. And it's heavy enough to accelerate the right-hand block, MB, up the incline. Right, so there's B. These angles are angle theta. And you can see all blocks start and end at the exact same height. Situation 2 has the same masses, but the ramp is not as steep. So if we were to call this theta 1, theta 2, and theta 3, theta 1 is the same angle as theta 3, but this is this angle is smaller, so these are greater than theta 2. So I'm kind of noting down the information, and then they say that the right-hand mass here is larger in this situation. So MB in number 3 is greater than MB1, which is the same as MB2. So these are some of the givens that are here. So the first thing, in which situation does the system have the lowest acceleration? This is a paragraph response, but that doesn't mean that it isn't useful to draw a free body diagram and get an expression. So that's what I'm going to do. I need a little more space, so I'm going to take another sheet of paper. And I'm not going to draw a different diagram for each. I'm going to draw one diagram and just note these differences, because this part, right, we've got MBG, right? This is the guy on the incline, and it's attached to this one. So I'm going to solve this as a system with my line of action in the direction that they say it's moving. Okay, so my line of action, since it's moving up the incline, they tell you that. So then I'm going to do this as my line of action. Okay, let's keep that clear. And then when I write out my net force equation for my line of action, this force here is going to break into components. I'm going to have MBG on the Y, and you can call it F sub G, that's fine also. Okay, so I have those. So on the line of action, I've got this pulling in the direction of motion, and this is opposing that acceleration. This is the total mass. So when I rewrite this, first of all, the x-axis, right, the x component of this weight is sine of the angle, and then this is the total mass of the system that I'm exploring here. So I end up with this expression, and I can divide both sides here. So this is my expression for acceleration in general terms. So now let's make a proof to answer the question, when is this acceleration going to be lowest? So we're going to look at these different variables. The ones that are changing are theta and the mass B. So we have to examine both of those to see what's going to happen, okay? We know that MA is always the same. So we're not going to be changing this term here or that term, right? So MAG in the numerator and MA in the denominator are constant. Now that might seem like no duh, but it's kind of useful to state. Okay, so now what's the effect of changing theta? So theta is only in one place. So when you have one of these here, the second one where the theta is smaller, so when theta goes down, what happens to sine of theta? That's also going to go down. You could check that on your calculator if you want to. Right? So when this goes down, this goes down. Therefore, this term, negative mbg sine theta, goes down. That means you're subtracting a smaller value from the unchanging MAG, we already did that, means acceleration will go down. So we now know that in this case, right, we're going to have a subtracting a small term. Sorry, I said that completely backwards. That acceleration is going to go up, right? I'm subtracting a smaller term, so acceleration goes up, right? Okay. So now, therefore, right? So therefore, we know that A2 is greater than A1. Okay, so we got that part. Now let's compare A1 to A3. So what happens when you change, because we can't compare 3 and 2 because there's mass is different and the angle is different. So we only want to change one variable at a time. So we're going to look at these two. So what happens if we are going to have a bigger mass but the same angle? So when MB goes up, let's look what happens, right? This term, MBG sine theta, goes up, and, right, MB goes up. But this is in the denominator, and this is in the numerator. And you can see that this one is multiplied by 10. This will be 10 times bigger than that. Yes, there is also an angle, but the angle is constant for both. So when you're increasing this, it's going to increase much faster than the one in the denominator. So what's the effect of that? Therefore, A, right, when the mass is bigger here, right, so that's in 3, is going to be smaller than A1, right? And that's because you're going to be reducing this numerator by a lot, okay, because you're subtracting a bigger number, so the acceleration goes down. So let's put these things together. So if we know that A2 is greater than A1 and A1 is greater than A3, now we can rank them. So A2 has the biggest acceleration. And there's the answer to your question. All right, so let's do part B. So for this, we know for all V initial equals 0. Okay, and the question is asking you which situation does the system have the highest velocity when the right-hand mass makes it to the top of the ramp? So we know they get to the same height, but we can see that this length, right, let's call it X here. We'll call this X2, X1, X3. So X2 is greater than X1, which is equal to X3. That's related to the angles, right? So what do we have here? So we already know that A2 has the biggest acceleration. If it's going to have the biggest acceleration, and, right, we know number 2 has the biggest acceleration, plus, has the biggest acceleration, plus it has the most distance during which to accelerate. It will have the biggest final velocity. Not just a little bigger, but a lot at the top of the ramp. So you can also look at this more quantitatively. If you look at this equation, they all start at rest. So your V final is going to squared equals 2a delta d. So for number 2 has the biggest here and the biggest thing here. Therefore, its final velocity is going to be biggest. All right, next problem, next part. Examine the situation you chose as an answer to part A. Now, there is now friction on the surface with a coefficient of kinetic friction between the ramp and the right-hand block equal to mu k. Derive an expression for the acceleration of the block in terms of all those variables. So let's practice doing that. We actually can just use this one as a starting off point. We already have this free body diagram already created. The only thing that we're going to add to it is friction. So we're going to say that there's now a friction force added to it. And so when we write out this expression, we're going to get MAG minus MBG sine theta minus friction over MA plus MB. So that gives us our line of action equation. And then you need to get rid of F because that's not one of your givens. So that means we need to use the y-axis. That's this one. So we have Fn minus mbgy equals 0. So Fn equals mbg cosine theta. So friction is mu k, which is one of the givens. See, it's right here. Times mbg cosine theta. Sorry, I forgot to write out the friction equation. Okay, so we just substituted that there. So now this can go in there. We've got this really kind of messy, ugly equation that you might recognize from other problems we've done. This routine, comes up a lot. And a lot of times, most of the time on the AP exam, they really don't put numbers in. So you have to really get comfortable going through this, which is why I keep asking you to do this over and over again. So here's the expression, right, for the acceleration of the block in terms of, now let's go through. We have got mu, g, ma, mb, and the angle, theta. So we don't have anything else except the things that are allowed. Always check, because the biggest problem that I notice with students is leaving in F as a variable, even though it's not listed, for example. All right, sketch a velocity time graph for the system, both with and without friction on the axes below. So for this one, let's think this through. We've got, we know it starts at rest here. Well, let's first label our axes. So this is velocity in meters per second, time. Do that first before you do anything else. And we want to mark important points. We've got this. We've got V final and half V final. We've got, I don't know, let's do it like this. Oops. T final, half T final. Right? You don't have any numbers, but you can use symbols, and it's better to do those things first. So with friction, I might start at rest and let's do without friction first. We're going to go from to time final, end up at V final. We're going to be here. So this is with friction. And with friction, what's friction going to do? And remember, the slope of a VT graph is acceleration. So what happens to the acceleration here is that you have another term, this friction term, and it's going to reduce your numerator, which is going to reduce your acceleration. So you want to show, it's probably not by half, but probably this is going to be with friction. And if we kind of look at this derivation, look a little bit at this derivation here, you can see the acceleration is related to V squared. This is not important. We're not doing this to scale. We're just doing rough. It's going to be smaller. okay? And if it's V final, actually this is probably a better relationship to look at because this is the slope in the same amount of time. When the acceleration drops, you're going to have a smaller V final. So you can write this out. This is a good mathematical model to use for this graph. All right, last question says below is a graph of acceleration versus mass A, which is the hanging mass for the system without friction. So we're back to the without friction example, not this one. Is this graph a correct representation of the relationship? Note that the x-axis expresses mass A in terms of mass B. Okay, so let's take a look. So the first thing I want to do, I'm going to note acceleration, that's mass A, and I want to look back at my expression for acceleration, which is mag minus mbg sine theta over ma plus mb. Okay, so let's think it through. Does this make sense? What happens, so what I'm going to do is I'm going to look at like different expressions. So let's say mass A is 0. If mass A equals 0, what would happen? If mass A equals 0, then my acceleration would be negative mbg sine theta over mb. Oh, this is a negative, right? These cancel, and we get acceleration equals to negative g sine theta. So can this be the right expression? No, because there should be a negative. Not correct, because acceleration should be negative when ma equals 0. Okay, what else could you do to figure this out? Well, when mb and ma are the same, what happens? Well, if MA and MB are the same, right, you're going to have MAG minus MBG sine theta. So you can just substitute MA in there for both. So that would factor out an MAG actually, and you could do 1 minus sine theta over 2MA. So the MA's actually cancel. And you get G over 2, 1 might, right? So look what happens here. You actually have a value for acceleration that, does that match here, right? So I guess it is going to definitely be in the positive region, right? So you could check that and see. It's going to be pretty small, but you can't tell size here. This is really your best feature to look at, that 0 point, that y-intercept. Should this slope be a constant slope? That's another thing you could look at. And you don't have to do all of these, right? One of these is enough to answer the question. And this one probably wasn't a great one to use. You also might want to look at what happens when MA is much, much bigger than MB, right? So when you have double, well, what happens to this equation when MA is twice MB? Well, this gets bigger and bigger. And if you kind of extrapolate, then MB gets negligible. These drop out. You end up with A equal to G, which means it's going to top off somewhere at 9.8. This means that you're not going to have a linear function. It's actually going to be at a maximum, right? Some maximum value. So you should have some sort of asymptote here that leads to, right? Well, obviously if B gets really small compared to A, it's just going to plummet as if it's in free fall. So there's so many different ways that you can look at this graph to see that this is not appropriate. And as I started to say before, you could also look at the general shape. Does it make sense that it's a straight line at all? You know, and you should be able to see that the relationship between acceleration and mass A is very complicated because it's in both the numerator and the denominator. So increasing it is not going to be just a linear function at all. It's going to be something kind of really messy. So we're going to leave it there. Going over this took 20 minutes. And so I would not be surprised if this took you, an entire period to work on. This is a pretty hard set of problems, but it's definitely at the AP level. And make sure you go through the scoring to see, listen, I didn't expect you to get all these right, but what you should see is that you're moving from developing level into proficiency. There's nothing in proficient that says you are correct. What it says is, while making an explanation or prediction, I can correctly choose or overtly state relevant physics in the form of definitions, laws, mathematical models, equations, and relationships. So you might have done, pieces of this correct, even if all of it wasn't correct. You may have done parts of this correct without getting every single part correct. So you want to just make sure it's overtly stated. That's really the big deal here. In the problem solving, did you show your work? Did you show a free body diagram? Did you write out the equation? Did you substitute in the values? Did you only use given values to do this stuff? If you did, right, and you generated an answer, then you're all good. You don't have to have a right answer, even if you made some mistakes, as long as you set things up correctly and you list and label what you've got. For the graph interpretation question, getting this one right here requires that you develop some sort of mathematical model from the trend line in answering the question. So that's what I was talking about. Like, did you examine, right, if this was appropriate in any way, like testing the y-intercept and talking about that, talking about the general shape by looking at if this is actually a linear function or not. Like, any of those things would bring you into proficiency. But even if you only chose any one of those, like you looked at a coordinate pair and plugged it in, you used only the y-intercept, you only talked about the graph shape, right? And so if you used them, but you didn't overtly develop the mathematical model, then you're in developing, okay? And lastly, with creating the graph, very importantly, did you label the axes? Did you put some sort of scaled values on the axes? Did you draw your trend lines and label them differently? Did you generate or at least list some sort of information about how you came up with this shape? So all of those things you'll see listed. The graph includes all the relevant features, plotted points, given reference values on the axes when appropriate. The trend line for the graph is selected based on an overtly stated relationship. So that's what you need to do to get to proficient, but if you didn't, that's something to work towards. Try to, always check back here to see if you've reached those levels, just so you don't freak out, right? Again, we're aiming for proficient. And some of you may still be in developing, especially for a few of these. That's okay. And also this one was a little bit long because I had two scientific explanation problems, one problem solving, and then one of each of the graphing ones. But it did have two of these for that, which make it a little bit longer. All right, let me know if you have questions, and I will try to help.